Oh, the word problems. Okay, so I guess I should start by telling you how to find the surface area of a rectangular prism. And I could have, do y'all know what it is? That's right. Yes. Are they coming from that way or they're coming from this way? Oh, that's so much fun. You think? Gathering. Okay. So, I know that y'all did not have the best. Some of us had some not so good geometry experiences. So, are they all over there? Is there a lot? Okay, but what I was saying is there are some geometry concepts that I know some of you might be lacking. We might need to concrete some of those. So I'm trying to intermingle some geometry in here too. So I didn't want to omit this question because it's important, especially for your standardized testing that you'll be taking and stuff. You'll see things like this. So surface area of a rectangular prism, so which is basically a three-dimensional box, right? A box that's rectangular in shape. And surface area is just taking the area of all the faces and adding it together. And so this is the short of it. 2 times length times width plus width times height plus length times height. You got to multiply them all together and then double them. So if I look, it says, and it really doesn't matter which one is which because you end up having to multiply them all together anyway, that the 3 different lengths are, so we'll say length will be x plus 3. We'll say width is x plus 7, and that leaves height as, I shouldn't do height, I should say that way, so I don't get mixed up with the L, x minus 1. And so now all I have to do is plug in, but I'm going to have a lot of multiplying here as I plug in. So the surface area of this rectangular prism is going to be 2 times, and I'm going to do length times width, x plus 3 times x plus 7. And then I'm going to do width times height, so x plus 7 times x minus 1 plus, and then I'm going to do length and height, so x plus 3, x. Okay, nothing to do it but to do it. I got this 2 on the outside. When I multiply these out, I get x squared plus 7x plus 3x plus 21. Does that make sense? I didn't draw the lines, but do you see what I did there? X times x, x times 7. I just foiled out there, essentially, is what I did. Plus, now go on to the middle one. X squared minus x plus 7x minus 7. And then the last one, x squared minus x plus 3x. Like terms, I'm going to do the like terms before I multiply by 2, because then I don't have to multiply as much by 2. So how many x squareds do I have? 3x squared? 7x, 3x, negative 1x, 7x, negative 1x, and 3x. What does that give you? Let's see. 10 minus 1 is 9, plus 7 is 16, minus 1 is 15, plus 3 is 18. All right, okay there? And then constants. 21 minus 7 is 14, and 14 minus 3 is, y'all can do that one, 11. Still have to bring that 2 through to everything. So 6x squared plus 36x plus 20. It was a whole lot of work for a simple little trinomial, wasn't it? Ah, that makes sense. Everybody see what we did? Oh, yes. Y'all done with that one before I scroll on past? Number 22. The area of a triangle can be represented by the expression 14x to the 5th plus 63x squared. And it says that the base is 7x squared. Write an expression to represent the height. Well, how do you find the area of a triangle? 1/2. That's right. Well, what do I have? I have the area and I have the base. Do we all agree? So let's just plug in what I know. I know the area is this. I know the base is 7x squared. Can you solve that for h? I hope you can. I'm going to get rid of this first. So yes, divide, or maybe it might be easier if I multiply it by 2, right? And if you put the 7.5 together and then multiply it by the reciprocal of that, that's okay too. I'm just kind of showing you step by step here. If you multiply both sides by 2, the half goes away and I end up with 28x to the 5th plus 126x squared. Now what do I do? Divide by 7x squared. And this is what we did yesterday. This is dividing a polynomial by a monomial. If I divide by 7x squared, what do I do? How do I simplify that left side? You break it up. That's exactly right. So I'm going to split it apart in 28x to the 5th over 7x squared plus 126x squared over 7x squared. That should equal h. So let's clean it up just a little bit. What's 28 divided by 7? 4. How many x's do I have? 3. 126 divided by 7? 18. And those cancel. They're the same, top and bottom. Just that because I'm multiplying, I'm not adding in here. So yes. Everybody okay? All right, I have to get my calculator. This is kind of a big day. Do y'all need a little break in between? Y'all generally have your break on the front end, so it's not quite as bad. First thing is polynomials, and we have talked multiple times about polynomials. We have defined polynomials, but as a more formal definition, I'm going to call this polynomial analysis. As a more formal definition, you have listed up here some things that polynomials have to satisfy. And it looks a lot worse than what it actually is. So we have this crazy looking function, a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus dot dot dot, which means continue on that pattern, right? A sub 2 x squared plus a sub 1x plus a sub 0. This looks quite intimidating, right? But it really doesn't mean anything more than you have n number of terms, okay? And each term has a coefficient with it. These numbers in front are coefficients. So this is the coefficient of the nth term. If I had 10 terms, say, this would be the coefficient of the 10th term, the coefficient of the 9th term, the 8th term, and so on until I get down to 0. So these are what I call coefficients. Just the A part here. But in order for this to be a polynomial, these coefficients have to be real numbers. So if you see an I for an imaginary number, I'm not a polynomial. Okay, it's got to be real numbers. The other thing that has to hold true, these exponents up here, not only do they have to be real numbers, they have to be positive whole numbers or integers. So what do I mean by that? What's it mean? 1, 2, 3, right. They've got to be positive whole numbers. They can't be fractions, decimals, anything of the sort. If they are, it's not a polynomial. So, for example, yeah. Tell me when you're done. No. Okay. Is that a polynomial? Yes, it is a polynomial. So check every coefficient. Are those real numbers? Yes. This is an irrational number, but it's still a real number. Are the exponents all positive whole numbers? Yes. What if I changed it? Is that a polynomial? No, this is not a polynomial. Why is it not a polynomial? These two exponents cause this to not be a polynomial. They're not positive whole numbers. Does that make sense to everybody? Everybody good? Say that again. Because the exponents aren't positive whole numbers. They're not integers. The exponents on x have to be integers. Positive. What is a sub n called? Look back at that intimidating type equation. What is this called? What'd you say? Leading coefficient. That's exactly right. So it's a coefficient, but it's the special coefficient because it's in the front of the equation whenever I'm in standard form. And we've already talked about leading coefficient. All right, a lot of this is going to feel like review here in the beginning, and it is a little bit, but that's good. All right, you got a table there with some examples of different types of polynomials that we are going to classify by their degree and their leading coefficient. There's a reason we're doing this, and you will see that in just a second. So you have function, and then you have degree, and then you have, I'm just going to put LC, leading coefficient. The first one is f of x equals 4. Is that a polynomial? Yeah, it's one term. The variable, if it had a variable, it'd look like that, right? Okay, what's the degree? And I kind of just gave it away. What is it? What's the degree? It's called a constant, yes, but what's the degree? 0. What is the leading coefficient? 4. And the type, of course, is, we said, constant, right? And in fact, I'm going to add a column on here and put type. Even though we've already done this, if you don't need that on there, that's fine. I just want to make sure I kind of hammer that home because that's going to be part of your analysis. But what we're fixing to do, we're really going to need just these two columns for. All right, the next one, f of x equals negative 5x plus 1. What's the degree? 1. What's the type? Leading coefficient? Negative 5. Oops, that's not the next one. 12x squared minus 11x plus 31. What's the degree? Leading coefficient? Type? Quadratic, that's exactly right. Next one, negative x cubed. Y'all can, I'm sure y'all can figure these out from here and don't need me to go through. That's okay. What's the degree? Leading coefficient? -1. A lot of you missed that on your quiz yesterday. -1 because there's nothing there. And how about the type? A cubic. -3x to the 4th plus x squared minus 18. What's the degree? Leading coefficient? Type? Quintic. Quintic. That's exactly right. That is a trinomial quintic, or a quintic trinomial, because it only has 3 pieces. And then the last one, 9x to the 5th plus 2x to the 4th minus x cubed plus 9x squared minus 2. What's the degree? Leading coefficient? Type? Quintic. Exactly right. Y'all had some crazy spellings for quintic yesterday. Degree. It's based on the highest exponent. Yeah. Hey, find what? The biggest exponent is the degree. So the biggest exponent was 5, that's the degree. 4, that's the degree. All right, everybody good? Say that one more time. Leading coefficient is the number, the coefficient hooked to the one with the degree. So this would be -1, this would be 12, -3, 9. All right, let's look at the parent functions. Again, now this is review from the last unit, but we are going to use all this, so we need to make sure you remember how to do it. What does the parent function of a constant look like? Or what's the equation, first of all? Y equals just a number, right? Or y equals 1, y equals some value. So we'll go with y equals 1. Just so you can see. So graphically, and we're not going to use our calculator for this because we know what this looks like. It's either or, same thing. Yeah. We should do f of x because that's more appropriate. At 1 and it goes across. So that's what the graph of a constant looks like, right? How about linear? What's the parent equation for a linear? That's exactly right. F of x equals x. So that's a y-intercept of 0, and it goes up 1 over 1. The constant should probably be f of x equals 0, but that's okay. How about quadratic? What is it? X squared. That's exactly right. That's my parent parabola that has a vertex at 0, 0, and has those points 1, 1, -1, 1, and comes out terrible parabola. We're getting into some you may not be quite as familiar with. What does a cubic look like? X to the third, and it looks like 0, 0. This was one of the ones that you had, and it kind of loops around like this, like this. It gradually comes out. It's not lying like that. And the more you stretch and shrink it, the more you do to it, the more these little pieces, a cubic can start to look like this, the more you mess around with the values there. But this is just the parent. All right, we have 2 more. These I don't expect that you know yet, so we need to look at them. What I do want you to do is take out your calculator, and we're going to graph them and look and then see if we can pick up the pattern. Can you guess what the parent graph of the Quintic, the equation, looks like? X to the 4th. All right, so take out your graphing calculator. And let's see. So let's do y equals x raised 2, so that's right there under clear, raised to the fourth. I want a normal window, just a -10 to 10, so I'm going to hit zoom, and then down here to standard, which is number 6. I hit zoom 6. Does your y equals look like mine? X to the 4? Are any of these up top highlighted? Go up, click on them, and hit enter to unhighlight them, and then come back down. Okay. Wonder what's happening with this graph. I'm going to hit this window button. You don't have to do this on yours. If you want to play around with it, though, with me and see what's happening, I kind of want to zoom in. I want to zoom in and see what's going on here, if anything is going on. So I think I'm going to change my x. Instead of -10 to 10, I'm going to change it maybe -2 to 2, and the same for y. So I'm going to hit window, and I'm going to go -2 to 2 for x. And then for y, I'm going to go -2 to 2 and just see. See how it looks like it's kind of laying down there? It's kind of hugging that axis a little bit. Maybe even if I zoom in some more. Interesting. And we're going to see how this changes and what this does the further we get in. For right now, the reason we're doing this is based on in behavior, which we're fixing to get to. So for right now, if I'm sketching the parent graph, I think I will just go with a little sketch. I know 1 to the 4th and -1 to the 4th is 1. I know 0 here, but I see it doing something a little bit different than a parabola. It looks like it's kind of coming down and smushing down, something about like that. Now, as we start moving this around and shifting it, this is going to start looking more like this sometimes. It can have the humps in it that way, just so you know and you are aware. But the parent graph itself looks more like this, where it's smushed out like a pancake there along the x-axis. Everybody okay there? All right, let's do the quintic. What do you think the parent equation is? X to the 5th. So again, I really want to graph this on my calculator and see what's happening. Any guesses? Nobody? I'm going to start with a standard window again. It looks a lot like the cubic. It absolutely does. But I'm going to zoom in a little bit on this one as well. I'm going to do my -1 to 1 again. Just see if I can kind of see what's going on. It looks again on this one like it's flattening out there. And it's doing the exact same thing that the Quintic was doing, is it flattens out. Is it could have some extra humps as I start messing around, some maximums and minimums and things like that we will talk about. So for now, though, I'm going to graph it similar to the Quintic, but it's got kind of that smushed pancake looking part here right along the axis. I didn't like that. And so, but just know, as I get further and further in my polynomial analysis, this could do something like that. Okay. In fact, each degree I add adds a potential another hump to it, if that makes sense. Because if you think about the cubic with the 2, the quadratic with the 1, Quintic with the 3, Quintic with the 4, every time I add a degree. So if I had a power of 6, it could potentially look like that. Okay, so every time I add a degree, I add one more little bump to the graph, essentially. All right, is everybody okay? Yes, no, maybe so. All right, we're going to try to figure out, and then I will let you take a break. We're going to try to see if we can figure out some generalizations about some end behavior. So look at number 1. It says use your graph and calculator to determine the end behavior. So the first one is 4x to the 4th, 4x to the 4th plus 6x cubed minus x. So let's graph it. Y equals 4x to the 4th plus 6x to the 3rd minus x. Is that a polynomial? Yes, it is a polynomial. They're real number coefficients, positive whole number exponents. I'm going to hit a zoom 6 just to give me back to that regular window I'm used to using. Ooh, little funky on the inside, right? But remember, this is a Quintic, so it could have those. It could look like a W almost. In fact, you don't have to zoom in, but let me just zoom in because I feel like you might not believe me. Just so you can see a little bit better. Do you see how it's the little humps are starting to form there on it? That indicates that it's a Quintic. Now, I don't have to know any of that for this question. This question just said, use the graph to determine the end behavior. And so you've got two. Do what? I changed my window a little bit. As x approaches positive infinity, looking at this graph, right? Looking at this graph, as x approaches positive infinity, what side of the graph is that telling me to look at? The right side of the graph. So as x goes to positive infinity, what is my graph doing? Is it going up or down? It's going up, so this would be infinity. Does that make sense? The second line says as x goes to negative infinity. So as I go further and further this way, what is that side of the graph doing? It's still going up. So in fact, both of these are positive infinity. Does that make sense? Remember when we did the end behavior? Okay, look at number 2. Number 2 is negative x squared plus x. What's happening here? Both ends are going down. Do you agree? So what should both of these be? Negative infinity. That's exactly right. Look at number 3. 2x raised to the 3rd. Graph. Ooh, this one's different. Both ends are not going the same way here. It's a cubic. As x approaches positive infinity, what is the graph doing? As x is positive, that tells me which side. The right. Is the right going up or down? Up. So this first line is positive infinity. As x approaches negative infinity, so the left side of my graph, what is it doing? It's going down. So that would be negative infinity. How about number 4? I'm going to let you do 5 and 6 on your own, but there's a reason I want to get through 1 through 4. Negative x to the third. Now, before you graph it, what do you think the difference? Well, never mind. What's the difference in the parent graph and this one? It's negative. What does the negative in front do? Reflect over x, right? So it should be flipped. So let's see if that's what happened. Looks the opposite, right? So as x approaches infinity, which means on the right-hand side of the graph, what is it doing? It's going down. So this first one should be negative infinity, right? How about the left side of the graph? As x approaches negative infinity, so I'm on this side, f of x is going up, which is positive infinity. Remember doing this? We looked at the graphs a little bit. So here's where we're trying to make a generalization, okay? I want you to notice a couple of things. Numbers 1 and 2 are both even degrees. Do you see that? Number 1 is 4x to the 4th, and number 2 is negative x squared plus x. Both of these have even degrees. And what did we notice about both of those end behaviors? They both went in the same direction, right? This one, the fourth one did something like this. The negative x squared one did something like this. But what I noticed is that both of them went in the same direction. They might not have always be up or always be down, but they both go the same way. Now, look at your leading coefficients here. When it was positive, they both went up. When it was negative, they both went down. This is a generalization for all polynomials that are even degreed. So look at your little chart. What's your degree of your polynomial? Okay, and which are both even numbers, right? So every time you have an even degree, both ends are going the same way. They're either both going to go up or both going to go down, okay? If my degree was 6, if my degree was 8, if my degree was 100, both ends are going the same way. I just have to determine which way. So in your box, you've got a box there, and it says positive leading coefficient, and then it says negative leading coefficient, and it says even degree, odd degree. I know that for even degrees, the ends always go the same way. If my leading coefficient is positive and my degree is even, then both ends are going to go up. What do you think happens if that leading coefficient is negative? They both go down. That's exactly right. Now let's look at the odd degrees. What did you notice? So this was like number 3 and number 4. What did you notice about odd degree polynomials? So a cubic parent graph looks something like this. The quintic really smushed out, right, but looks something like that. I could make it negative in front and it'd flip around, but both ends, no matter which one it was, went opposite directions. Do you agree? But I just have to decide which one goes which way. So if this was x cubed, right, that's what the parent graph looks like for x cubed or x to the fifth. Well, then if the leading coefficient is positive, it goes up on the right and down on the left. Now, when you graph negative x cubed, it went the other way. So negative x cubed did something like this instead. So for negative odd, as x goes to infinity, it's just the opposite. But both ends are still going different directions. And this chart holds true for any polynomial in the whole world. So I could say, what is the end behavior of f of x equals negative 75x to the 25th plus 16x squared minus 5? What's the end behavior? Any guesses? Is it even or odd degree? One's going up and one's going down. Which one's going which way? Well, it's an odd degree, right? Because 25 is an odd number. So I'm in this column, and now is it positive or negative in front? Negative. So this is the end behavior for that polynomial. The right side is going down and the left side is going up. I don't know what else is going on with this crazy polynomial, but what I do know is the right side is going down and the left side is going up. Whatever else happens in between here, I don't know, but that's what the ends are doing. Does that make sense? I know I've talked a long time, and I promise I'm almost done. Look at number 7. It's a graph that looks something like this. Do you think that is an even or an odd degree polynomial? Why? Look at y'all. Do you think the leading coefficient is positive or negative? Why? See where we're going with this? Look at number 8. Odd. Why? Ends are going different directions. Do you think the leading coefficient is positive or negative? Ooh, I heard both. I would say positive. I always think about a line. Linear is an odd degree, right? So a positive slope looks like that, and a negative slope looks like that. A positive slope would be a positive leading coefficient, a negative slope would be a negative leading coefficient. Or if you have to think about the general cubic. Okay. It'd be positive because the right end is going up and the left end is going down. Oh.